Hi, it's Mr. G. In this lesson, I'm going to show you how to use the mole in conversions that involve compounds and molecules. And what you're going to find is these conversions are no different than the conversions we did before with the mole involving atoms and elements. However, the one thing that is different is we simply use the molar mass of a compound as opposed to the atomic mass of an element when converting between moles and grams. So if that confuses you a little bit off the bat, that's okay. Let's go ahead and work the problems, and I think you'll see that these conversions are going to look very similar to the ones we did before. So the first type of conversion that we're going to do is a conversion between the moles of a substance and the grams of a substance, where our substance, in this case, instead of being an element, just an element, it's actually going to be a molecule as well as an element. I'll show you what I mean. So our question says, how many grams of hydrogen gas are present in 4.26 moles of it? One of the things that we should understand now about hydrogen gas is that hydrogen gas is not just plain old H. Remember, hydrogen is one of those diatomic elements. What that means about hydrogen is when we write it out, and when it exists in nature, it exists as a pair. So that means there's two of them bonded together to form a molecule. Not a compound, but a molecule. And that changes the nature of this question. So remember, it wants us to know how many grams are in 4.26 moles of it. So that means we're converting from moles to grams. And whenever we go between moles and grams of a substance, we need the molar mass. Right? Before we learned about the fact that molecules and compounds could have a molar mass, we would just go straight to the periodic table for an element and get its molar mass. But since this is a molecule, we still go to the periodic table, and we know that hydrogen's atomic mass would equal its molar mass. But in this case, we have two hydrogens that make up our molar mass. So we multiply it by 2. Because there's two hydrogens combined in our molecule to make up the total molar mass of the molecule. So it's 1.00794 times 2. That gives us a molar mass for H2 as 2.01588 grams per mole. So we know that 1 mole of H2 gas will equal 2.01588 grams of H2 gas. And that is going to be our conversion factor we use to convert between grams and moles of the molecule. Right? Now, our problem is no different than any other conversion problem we would do. We write out what we're converting from, which in this case is 4.26 moles of our substance, which is hydrogen gas. We recognize that this unit must go on the bottom because we need to cancel it out. So moles of H2 gas. We find in our conversion factor where that is. Moles of H2 gas is here, so the 1 goes on the bottom. We know that what we're converting to is grams of H2 gas, so we put that on top. And we know that the molar mass is what's associated with that unit of grams of H2 gas, so the 2.01588 goes on top. You can't forget about significant digits. We know that there are 3 in this number, and there's 1, 2, 3, 4, 5, 6 in this number. So we're going to have 3 in our final answer. So we go by the least amount. So we'll do our multiplication. It'll be 4.26 times 2.01588. And I get an answer of 8.59 grams of hydrogen gas. And that's how many grams are present in 4.26 moles. Next, so that's a mole to gram problem. Now if we're going to do moles to molecules, well, let's take a look. How many molecules of C2H2 gas are present in 8.26 moles of it? Well, I'm starting from moles. And I want to go to molecules. Well, here's the great thing about these problems. They are identical to the problems where we go from moles to atoms. Because remember, a mole is just a counting number. It's like a dozen of something, right? It can be a thing. You can have a dozen eggs, you can have a dozen tables, you can have a dozen chairs. Well, we can also have a mole of tables, we can have a mole of eggs, we can have a mole of atoms, we can have a mole of molecules. It doesn't matter. So our conversion factor is the same. 1 mole, in this case it's C2H2 molecules, is still going to equal 6.022 times 10 to the 23rd C2H2 molecules. It's the same identical type of problem that we did before. It's just using molecules instead of atoms. It could just as well as have said how many elephants of circus elephants, how many types of circus elephants are present in 8.26 moles of circus elephants. And we would be solving the same problem. So we need to understand that fact, and all these problems end up being the same thing, really. So we know our conversion factor, we do the math the exact same way, we take the number we're starting with, we know that moles is on top, and it must therefore go in the bottom of our conversion factor, because again it needs to cancel out. Since we know it needs to cancel out, that means we find where it is, moles, okay, the 1 goes on the bottom, that means. Alright, we want to go to molecules, so molecules must be the one that's going on top. Okay, we find the number that's associated with it, which is Avogadro's number. That goes on top. So this is telling us we're going to end up multiplying the 2 numbers to get our final answer. Right? Because these units cancel, which means we'll end up with molecules. So our math is just going to be 8.26 times 6.022. I get 49.7 because I'm doing this to 3 sig figs times 10 to the 23. We want to move our decimal point over to the left. We want to make our exponent larger. That gives me 4.97 times 10 to the 24 molecules of C2H2 gas. And that's the answer. Alright, let's try a different type. All right, how many moles of hydrogen cyanide are present in 6.84 grams of it? All right, we always want to ask what we're starting, where we're going. So from, right, converting from, I know I'm starting with this certain number of grams, so I'm converting from grams. What am I going to? Well, looks like moles. From grams to moles. Okay, well, I know that in order to get between those two things, I'm going to need molar mass, right? And I need to go to periodic table for molar mass, and this time it's of a compound. All right? My compound has one H in it, one C in it, one N. For this, I need my periodic table, right? I have memorized that hydrogen is 1.00794 grams per mole. I have memorized that carbon is 12.0111 grams per mole. I know nitrogen is 14. I think it's 0067, but I'm going to double check myself because I can't exactly remember. It would be files, I do believe. Let's take a look there. Yep, 14.0067. It's always good to double check yourself. 0067 grams per mole. Alright, so I need to add all these up and get the sum to get our molar mass. I know that my line is going to be here for sig figs. Sig figs always matter. 14.0067 plus 12.0111 plus 1.00794. And I get a molar mass of 27.02574 grams per mole for hydrogen cyanide. Alright, so now I have what I need. I just need to set my problem. Let's get our periodic table out of the way. So I know I'm going to convert this number 6.84 grams of HCN, and that's going to be converted to moles, right? Well, I know that the grams of HCN needs to go on the bottom for it to cancel out. I should probably write my conversion factor over here just to make sure I'm doing this right. It's good to have your strategy done the same way every time. So we know that this number to that many significant figures, grams of HCN, equals 1 mole of HCN. That's my conversion factor. Alright, so I know that the grams is on the bottom, which means this is the quantity that goes on the bottom. 27.02574 to that many sig figs, which is 1, 2, 3, 4, 5, 6. I'll even write the 6 on top so I can keep track. I know that that's 3 sig figs there, so I'm keeping track. And then the 1 mole will go on the top of HCN. Let's cancel out our units. We know that we're dividing 684 by the molar mass of hydrogen cyanide, 27.02574. And that gives me 25.3, because we're doing this at 3 sig figs, and I'm rounding that off my calculator, grams of hydrogen cyanide. That's a lot of hydrogen cyanide. That stuff is nasty. It'll kill you. Alright, 25.3 grams of hydrogen cyanide. Oh, no, this is moles. See? Check ourselves, right? Moles. We are going from grams to moles. Here we are. moles of hydrogen cyanide. Okay? 25.3 moles. Alright, so for this problem, we're going to be converting from grams, it looks like, of a substance to molecules. It says how many molecules of hydrobromic acid are present in 12.01 grams of it. Well, so we're converting from grams all the way to molecules. And if we're going to go from grams of something, we can't go straight to molecules. Remember, we need the mole as a bridge to get us there. And so that means we've got to go from grams to moles first using the molar mass. And then we can go from moles to molecules using Avogadro's number. And so we know that 1 mole of this hydrobromic acid, we already know that that's going to equal 6.022 times 10 to the 23rd molecules of HBr. We've already got that figured out. What we don't have figured out yet is the molar mass. We've got to go to the periodic table for that and add up the atomic mass of hydrogen, which is 1.00794 grams per mole, plus the atomic mass of bromine, which I know is 79 point something. I need to look the rest of that up. Existing, oops. Let's see, 79.904. So 9.904. 904 grams per mole. So we can add those two up. Not forget about sig figs. And we'll get our molar mass for our hydrobromic acid. So ends up being 1.074 plus 79.904. Just double check myself. 89.9194. Yes. Okay. Grams per mole. There's our molar mass. So now that we've got our molar mass, we know that's our first conversion factor, that 89.91194, that's to 1, 2, 3, 4, 5 sig figs of grams of HBr, hydrobromic acid, will equal 1 mole of hydrobromic acid, where 1 mole of hydrobromic acid equals 6.022 times 10 to the 23rd molecules. We've got all of our conversion factors nicely laid out. We can now do our conversion using our 12.01 grams of hydrobromic acid. We know grams of HBr has to go on the bottom, so it cancels out. That means that the molar mass goes on the bottom. So we place 89.911194 in the denominator. We place 1 mole of HBr on top. We know those two cancel out. Can be done with this kind of part of the conversion factor. Now we're left with our second part. We know that mole of HBr must go on the bottom. And that means molecules must go on top. Leaving Avogadro's number on top. We can cancel them out and do our math. We're going to multiply across the numerator, 12.01 times 6.022. That is 72.32, we'll say 4 to that for our sig figs. And then we're going to leave our exponent times 10 to the 23. And then we are going to be dividing by 89.911194 to the 5 sig figs. This is all with molecules of HBr. Let's do our division now. We'll get 0.804396 times 10 to the 23rd. We want to simplify that into proper scientific notation and to our proper number of sig figs, which will be 4 sig figs because of the number we started with and because of Avogadro's number. So that's 1, 2, 3, 4. We're going to round up. So if we go to the right, we're going to reduce to 22. So our final answer, I'm going to bring it over here, will be 8.044 times 10 to the 22 molecules of HBr. All right. Let's take a look at the next one. So here, how many grams of methane are present in 1.08 times 10 to the 24 molecules? So it looks like very similar to the last one, but we're going in the opposite direction, right? We want to know how many grams, but we have molecules. So this time, we're going from molecules all the way to grams. And like the last one, that means we still need our bridge of moles in between to get us to where we want to go. This just means our first conversion factor will be our Avogadro's number, 6.022 times 10 to the 23rd molecules equals 1 mole. In this case, it's CH4. And then here we have to do our molar mass. Carbon and hydrogen times 4 is going to be how we're going to have to handle this problem. So 12.0111 plus 4 times 1.00794. So 1.00794 times 4. So I'm just going to cross that out and replace it with but it is multiplied by 4, and that is 4.03176. We'll draw a line for our sig figs. Make sure I've got everything lined up properly. And we'll add it to 12.0111. We have 16.04286 grams per mole. Just checking myself in my head to make sure it makes sense, and it does. Always a good thing to do. Alright, so that means our molar mass, of course, 1 mole of CH4 will equal 16.04286 grams of CH4. Oops. And that's going to be to 1, 2, 3, 4, 5, 6 sig figs. So now we have everything laid out, we can do our conversion. So let's go ahead and convert our 1.08 times 10 to the 24 molecules of CH4 to our grams of CH4, which is methane, by the way. It's what's in our Bunsen burners and in most of your gas stoves if you have gas stoves at home. So molecules of methane is on top. That means molecules will be in our denominator. And then 1 mole will go on top for CH4. And 6.022 times 10 to the 23 will go on the bottom. That's our first conversion factor here. And then that means moles of CH4 will go on the bottom here, because they need to cancel. The 1 will go there, and then our molar mass of methane will go on top. 4.286, and that is 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 sig figs there. Our final answer will be, though, to 3 sig figs. Alright, so let's do our math. We're going to multiply across the top. 1.08 times 16.04286, and then divide that by 6.022, leaving us with 2.883 sig figs. We're going to have to do 24 minus 23 because of our exponents, which leaves us with a 1. So our exponent will be times 10 to the 1. And that is, of course, I'm going to cancel everything out. I didn't even put my units here, which should be grams of CH4, and that will be our unit, grams of CH4. Well, let's get that exponent out of there, since it's only times 10 to the 1. I'm going to reduce that down to 0, so I'm going to move that to the right. So that means our final answer should be 28.8 grams of CH4, otherwise known as methane. So as you can see, these problems are no different, really, from the other ones that we did in our last unit, other than the fact that our molar mass, again, is just the molar mass of our compound or molecule that is added up from the compound or molecule's constituent atoms from the periodic table. Alright, one last practice problem. How many moles of ammonia NH3 are present in 5.01 times 10 to the 23 molecules of it? So here we're going from molecules to moles. Or, yes, molecules to moles. We have molecules, and we want to know moles of ammonia. all the way to moles. Right? Well, hopefully we recognize that the conversion factor for this is quite simple. Avogadro's number, right? 6.022 times 10 to the 23rd gets us between things, atoms or molecules, and moles, right? So we have 5.01 times 10 to the 23rd molecules of this NH3, otherwise known as ammonia. And that brings us to needing to put molecules of ammonia in the denominator, so it cancels out. And that puts us with moles of it on top. So 1 mole okay, that's how it works. 1 mole makes 6.022 times 10 to the 23rd molecules. So we end up dividing 5.01 divided by 6.022, and the 23's will cancel out since we're doing 23, 10 to the 23 divided by 10 to the 23. So it's just 5.01 divided by 6.022, and that will give us our moles. We want it to 3 sig figs, right? Because that's the least amount. I get a number of 0.832 moles of ammonia. And there we go. All right, so 6 example problems. I know that's a lot of examples, but they give you each scenario that you could ever come across. Every type of problem you could get with these. Make sure that you practice, okay? If you didn't get these types of problems on the last test, and you didn't do your test corrections, then you're probably going to get stuck on all these too, okay? So you still have time to do your test corrections from the last test, which is only going to help you get these problems right on the next test, okay? I told you that this stuff wasn't going to go away. Well, this is why. So if you were squared away on the last test, now that you've maybe you've done test corrections, you feel more comfortable with it, maybe you identified that it was just sig figs or whatever. These problems are just the same. The only thing we're adding in there, again, is this molar mass. And it's a new concept that, hey, it's not just elements anymore. It's these things called compounds that we can do the same exact thing with. Same math though, right? Same ideas. Your turn to practice.